let's put all of our knowledge to use to find and sketch this rational function right here. So what we have is f of x equals x minus 2, x minus 3 over the quantity x plus 1 squared times the quantity x minus 2. So we're going to graph all that, and we're going to do it following these steps. Domain, asymptotes, holes, this should say vertical asymptotes, horizontal asymptotes, and then we're going to sketch it. Okay, we're going to put all of that stuff together. On the side here in the boxes is stuff that we have covered in previous videos. Okay, it's typically the one just before this. So we have walked through how to find all of these items. So now we're going to put all of them together in one problem and sketch a rational function. Okay, so first things first, we're going to find the domain. Okay, I'm not allowed to have zeros in the denominator, so I can see just looking at this denominator, this can't be 0 and this can't be 0. So this means that x cannot be a -1 and x cannot be a 2. So the domain is the set of x values such that x is not -1 or 2. Okay? Excuse me. All right. Now, something to note here, simplify this if possible, and we do this by factoring the numerator and the denominator and canceling any common factors. So it's already nicely factored, okay? And I can see that I have a common factor here and here. So just like simplifying fractions, right? With just numbers, we can simplify rationals, okay? So my simplified version of this is x minus 3 on top and an x plus 1 squared on the bottom. And this is as long as x is not -1 or a 2. Okay? All right. Determine any vertical asymptotes. Well, remember, a vertical asymptote, which means as x is approaching some constant, our graph is going to infinity or -infinity. Well, in shorthand, or let's jump down to the informal definition, this was exclusions to the domain that did not have common factors with the numerator. Well, these were common factors. So which one didn't? The -1 is an exclusion to the domain that did not have a common factor. Okay? So that means that at -1 is where our vertical asymptote is. The one that did have a common factor, that is where there is going to be a hole. So those are two places on the graph where x doesn't exist, right? There's no x values. Vertical asymptotes and holes don't have x values, okay? So vertical asymptote is the vertical line x equals -1, okay? And since we're at it, there is a hole when x is 2. Now, I'm going to piggyback one more thing onto the hole piece. If you want to know like the y value of where that hole is, okay, you can plug that number into not the original rational function, but into the simplified one, okay? You're not supposed to plug a 2 into this simplified function, right? It's kind of like no, right? Because you know that this is the hole and this is a vertical asymptote. So technically, when x is 2, there is no y value. The simplified version doesn't know that, though. So if I plug a 2 into there, my top becomes -1, and my bottom becomes a 9. 2, -1/9. That will be where the hole is, okay? All right. Here's what we got. I'm going to come to oblique or horizontal in just a second. I'm going to come to my graph here. Draw my grid. Here is my x-axis. Y, I don't really know why it's missing a line there, but let's go right here with my y-axis. Okay. 2 Negative 1/9 right there is where there's a hole in my graph. It should even be up a little bit higher. All right, and then I have x equals -1 is where my vertical asymptote is. Like so. Okay. Next, any horizontal or oblique asymptotes. So let's recap what we know about those. All right. And we can look at the simplified version anytime. Remember, there was a degree issue, right? If the degree of the numerator is 1 larger, then we have ourselves a slant asymptote. Well, we don't have that here. If the degree is, or if the degrees are the same, or the numerator is smaller, then we have a horizontal one. Okay, so I do have a horizontal one. I'm looking at the simplified, so it's going to be horizontal. By the way, if it was oblique, you'd have to do long division. Okay, so not oblique, we have horizontal. Now, we're going to look at this. As x goes to either a positive or a negative infinity, what is happening to f of x? Well, the controllers, right? The leading term on the top and the leading term on the bottom control the behavior. Oh. As x goes to infinity, that fraction goes to 0. So my horizontal asymptote is y equals 0. Which means right here, we have a horizontal asymptote. Okay? All right, and now we may need to find additional points like intercepts or others to sketch this rational function fully. So remember, our simplified function is x minus 3 over x plus 1. I think that was squared. I'm going to look up this one more time. Yes. All right. So let's suppose I was looking for the y-intercept. Well, we would plug in a 0, and we would get -3 over 1. Okay, so I know 0, -3 is on the graph. Right there. Okay. Now let's say we want to find, so this is y-int. If I was going to go after the x-intercepts, I would set it equal to 0. And when do fractions equal 0? When the top equals 0. So this happens when x is 3. So 3 out comes a 0. 1, 2, 3. So that's here. Okay. All right. So there's no other x-intercepts. So the craziest thing is I do know, just because there's no other x-intercepts, that the graph is going to do this. It's going to go here. It's going to jump over that spot. It's going to cross. But remember what we said for end behavior. It's actually going to cross, and then it's going to come and approach that asymptote in the long run. Now, typically, we don't have a lot of graphs that cross the horizontal asymptotes, but they can, and this one does. Okay? Now, if you're insecure about that, it's okay to do more data points, like 1, 2, 3, let's plug in a 5. So what is f of 5? 2 on top, 36 on the bottom. Yeah, that's really small, right? But it is above. And then if you wanted to try another one, let's say f of 10. We would have 7 on top and 11, 121 on the bottom. Well, that's even smaller. 5, what did I plug in? 10, 6, 7, 8, 9, 10. Yeah, so it's above, but really tiny. Okay. All right. Let's go on the other side of that vertical asymptote because there's a graph there. There's pieces of the graph there too. So let's try f of -3. -3 would produce a -6 on top and a 4 on the bottom. So this would give me a -1.5. 1, 2, 3, -1.5. Right? How about -2? Top would be a -5. Bottom is going to be a -1 squared. Oh, hey, it's at -5. 1, 2, 3, 4, 5. Okay, so what does this tell me? This tells me that my graph is gonna go like this, kind of. A little bit sloppy in it, but it's gonna approach the horizontal asymptote from that side. Okay, so it kind of looks like that. Now, if you have, this kind of just something to note, not something you have to memorize, because you can always do, data points. But if you have a repeated exclusion to the domain, right? So it's like x equals -1. Yes, it's a vertical asymptote, and it happened more than once down there. We had multiplicity. If there's multiplicity that's even, you're going to approach that asymptote going to either infinity or negative infinity on both sides. If it's odd multiplicity, then it's going to be one of each, one infinity, one negative infinity. Which one is on which side, you have to do data points to find. So, okay. Now, because it's kind of fun to see how close we got, I graphed, oh no, didn't lose it, did I? Close that ad. I graphed, side note, if you search free TI-84 calculator, you can get a free calculator to use, just web-based. Obviously, Desmos is a great one too. Lots of students have these in the classroom, so I tend to use this. All right, I inserted our original function on top, and I'm going to hit graph. And this does look like what I have graphed. Now, it is of note that the handheld calculators are not going to find your holes. Okay, the reason they're not going to find their holes is because they are programmed to find data points and then connect dots. So if there's a hole, it doesn't know that. It's going to connect dots. So at least the TI-84s, and I think even a few that are better, still won't find holes for you. Okay, so there's that. Now, let's see, one more thing about the calculators. This calculator, you can do the fraction by, in green, there's this x, t, theta, n button. You can see that there's a fraction notation there. So you can insert fractions. If you cannot with your calculator, because it's an older version or what have you, make sure that you're using lots of parentheses so that you don't have a parenthesis error creating havoc on your life. All right, let's do one more problem here on rationals. Excuse me. Okay, so here's a picture of a rational function graphed. And our job is to come up with the equation for it. There's no holes, okay, or not that we can see anyway. So if we can't see any, we're not having any, okay? And they want us to find the equation for it. Well, we know it's a fraction over a fraction because they're telling us it's a rational. And I'm going to zoom in to point out a few things, okay? I see a vertical asymptote here, okay? So we have a vertical asymptote at x equals -1. There's another vertical asymptote. It's not very obvious, but right here, oh no, right here. At x equals 2, okay? Now, it's not super obvious that we're crossing here, then it's kind of creeping back up. Here it's a little bit more obvious. We crossed a horizontal asymptote, but then it's creeping back down. So I'm going to say horizontal asymptote looks to be y equals 0, okay? It looks like, and more than looks like, a y-intercept at 0, -2. X-intercepts at -2, 0, and 3, 0. And that's all we know from the graph so far. All right, let's see. And our job is to come up, use what we know about rational functions and come up with our equation. So we're going to say f of x is equal to, now let's talk about what's not in the domain. The x's that don't have y's with them are a -1 and a 2. So that means I'm in the denominator going to put an x plus 1, because it has to solve to equal that, and an x minus 2. Okay? Now, there might be a number in the front here, so I'm going to say a. When the tops of fractions are equal to 0, that's when it's equal to 0. So my x-intercepts are going to be found when the top is 0. So that means I have an x, let's see, plus 2 and an x minus 3. Think about this. If I plugged in a -2 into the function, would you get 0 over some number which ultimately is 0? Yes, you would. Okay? Same thing with the 3. Okay. So now, looking at this though, if this is what I have, and remember, if the degrees are the same, so let's talk about leading term over leading term. So leading term top, leading term bottom. Right now, the leading term on the top is ax squared. The leading term on the bottom is x squared. Remember horizontal asymptote when we had that conversation? If you need to go back to the previous video, do that. Horizontal asymptotes, if the degrees are the same, top and bottom, then the horizontal asymptote would be whatever, the coefficients are. But ours is a 0, and I can't start with a 0 in front of this. The only other way to get a horizontal asymptote of 0 is to have a larger degree on the bottom. So that means there is one more quantity on the bottom that I don't have represented yet. But I don't have any other vertical asymptotes either. So that means one of these is repeated. Okay? So if that logic makes sense, let's go and talk about how I mentioned that if we approach a vertical asymptote and are going in the same direction, then that particular piece had multiplicity in the function's denominator. So that the fact that there's approaching 2, there wasn't one up, one down. It is both going down. So that means that x minus 2 happened either 2 times or 4 times or an even number of times. Okay? I'm going to make it just 2 though. Now, this will take care of the asymptotes, takes care of the y equals 0 asymptote, horizontal. I don't know a yet, and I haven't done anything with this y-intercept. Here's what I know. When I plug 0 into this, for an answer, I have to get a -2. Okay? There could be a multiplier in the front. We'll call it a. If I plug in a 0, I'll have a 2 there, a -3 there, a 1, a -2, and a -2. In other words, I'll have a -6a or a +4. And now we simplify, or solve for a rather. Multiply by 2, we'll get -8 equals -6a. A is going to equal a positive, wait, do I have a sign error? I know, it's 4, 3. 4, 3. Yeah. It's divided, it'll be a negative and negative. Positive 4, 3. So what does this mean? This means that my function, in order to get those data points, in order to get this vertical, these for vertical asymptotes, this for a horizontal asymptote, my function needs to be a 4x plus 2, x minus 3 over, I'll put the 3 in the front on the bottom, x plus 1 and an x minus 2 with a multiplicity. And there's that function. Is those tricky? Absolutely, they're tricky. But as you practice and you gain more experience, then problems like this get a little bit easier. So you got to practice the easy stuff first and build. All right.